Alright, so I am now using multiple pieces of software to try to get an acceptable video feed for you guys. Here's hoping. I'm going to pick up with torque with 11.2. We actually filled in this first part in class, but I'm going to go through it really fast because I'm then going to solve problems using it. Feel free to skip forward a few minutes if you are like, I remember this, Ms. Schneider. It was yesterday. Okay, so I told you that torque is the rotational, I'm really bad at spelling, equivalent to force. It's a force acting in a circle. And like forces cause acceleration, a single torque acting on an object causes an angular acceleration, which is alpha, or fishy, depending on who you are. When a force acts on a mass attached to a light rod, as shown over here, it causes the mass at the end of the rod to accelerate linearly, but it also creates a torque. So a force creates a torque, and the torque causes the rod to experience an angular acceleration about the pivot point, so about this point in the center. When a force is applied tangent to a circle, as shown in the diagram, the torque produced is just going to be torque equals the radius times the force. This radius, for the record, is sometimes called the lever arm because it's not always obvious that you're dealing with a circle, but it's how far you are from the point of rotation to where you're applying the force. If you're talking about torque, like trying to take the lug nut off of a car, your point of rotation is the lug nut. The part where you're applying the force is where you're holding the wrench. So if we're going to write net torque in terms of moment of inertia and angular acceleration, then it's going to be net torque equals I alpha. This can be, oh, you couldn't see what I was writing, net torque equals I alpha. This can be remembered because it's super similar to Newton's second law, which you really better know, which is net force equals mass times acceleration. The rotational analog for each of the variables is subbed in. The rotational analog for force, we just said, is torque. The analog for mass is rotational inertia, or since that's the way the blanks are set up here, it's moment of inertia. Those mean the same thing, which is I. And the analog for acceleration is angular acceleration. That one's obvious. Fishy. All right, so we're looking at these two systems, and we want to know which one's going to hit the ground first. So thinking about this, which one is going to have the greater moment of inertia? Well, moment of inertia depends on how far you are from, how far the mass is located from the axis of rotation. The further out, the greater moment of inertia. So this one's going to have so we can actually answer the second part of this question easier. The system on the right has the smaller moment of inertia. And so let's look at this equation. Which one is going to hit the ground first? Is moment of inertia going to cause something to move faster or slower? Well, it's equivalent to mass. The heavier something it is, and it's equivalent to regular inertia. Inertia is how difficult something is to get moving. So this one that has a greater moment of inertia is going to be harder to get moving. So this one's going to start moving first, which means it's going to hit the ground first. All right, then it asks us to solve that using numbers instead of just words. If the rod in the picture is essentially massless, which means we don't have to worry about the moment of inertia of the mass, which we would in real life, and the masses here are at 1/2 the radius over here. So this is R, this is 1/2 R. By what factor does the acceleration and time to the fall to the floor change, assuming the system to be at rest when the mass begins to fall? So let's look at that. First, let's look at the factor by which it asks about acceleration and time. Both of those, time is going to be dependent on acceleration. Acceleration, as you can see from here, is dependent on moment of inertia. So let's actually look at how the moment of inertia changes. And that's kind of important because they didn't ask how the moment of inertia changes. But that's going to be what we need to evaluate to find out what they want. So, using like the law of ones, this guy here is going to have a moment of inertia of 1, basically, because m's 1, r is 1 squared, because remember they both are going to have a moment of inertia of m r squared, m, you can't see what I'm doing, r squared. Why am I uppercasing only the r, not the m? Because I'm a mess. I guess I should be consistent. So here, 1 times 1 squared is 1. Here, the mass is the same, but the radius is 1/2, so the moment of inertia is actually 1/4 as much. Okay, so what's the acceleration going to be like? Well, if we rearrange this equation for acceleration, let's do that up here actually. It's alpha equals torque over moment of inertia. Now the torque here is coming from the force due to gravity, so the torque is going to stay the same for both of them. So when we're looking for alpha, and it's torque over I, and we're using the rule of ones, so the torque does not change, but we just found that the moment of inertia changes by 1/4. So we have 1 over 1/4, which equals 4. We've looked at this in class. Please don't look at that and tell me that 1 over 1/4 is 1/4. It's not. 1 over 1/4 is the same as 1 divided by 1/4, which is the same as 1 times 4 over 1, which is 4. So acceleration is 4 times larger. It's going to move 4 times faster, which is pretty crazy. To get time, we would need to think about those rotational kinematic equations we used. I'll leave it up to you to look at which ones we would need to use. The key facts here are that omega I is 0, so I'm not going to leave it up to you. I'm going to do it. I'm just going to tell you I'm going to leave it up to you. Haha, joke's on you. I'm doing it for you. What am I doing with my life? We know that this is 0. And we know that in both cases, the amount the two things are going to turn before it hits the ground are going to be the same. So that means that the angular displacement, the theta, is the same, which is important for us to be able to use the rule of ones. So we know how much alpha changes by, we know Wi is 0, we know that the change in theta is the same, and we're looking for time. You're going to end up wanting to use delta theta equals omega I t plus 1/2 alpha t squared. So if we're looking at that, delta theta isn't changing, so it's 1. That whole term is 0. So 1/2 is 1, which is one of those things that's super hard to remember when you're using the law of ones. I just confused myself, sorry. So 1/2 becomes 1. Alpha becomes 4. And you have t squared. So then we need to solve that for t squared, and we get t squared is 1/4. You can't see what I'm doing. Which means that t is 1/2. So the time is going to take, it's going to take half as long. It's going to accelerate 4 times faster, and it's going to take half as long. That's why, again, it's such a big deal where things are located in terms of moment of inertia. All right, let's look at example problem 8. A 0.6 millimeter rod that's light has compact 500-gram masses attached to each end. The dotted line shows the position of the axis of rotation in the 3 cases. Rank the 3 cases in order of increasing angular acceleration, assuming equal torque is applied in each case. You may assume that the pictures are roughly to scale. So if the pictures are roughly to scale, I'm going to somewhat arbitrarily call this R, because that's the distance from the mass to the axis of rotation. Here, if they're to scale, then this looks like it's about 2r, the distance from the mass to the axis of rotation. Here, this picture confused me for a minute. I was like, what is it showing? What is happening? I think that it's rotating this way, as in the axis of rotation is through the bar, and the bar is just like turning. I have no idea if you're going to be able to see that I'm like turning my pen. Woo. So your R is tiny because it's the distance from the center, the axis of rotation, to the edge of the compact mass. R is basically 0. So then if you think about this, the larger the radius, the greater the moment of inertia. The greater the moment of inertia, the smaller the angular acceleration. Okay, sorry, I paused for a minute to unconfuse myself. So yeah, they want angular acceleration, which is inversely proportional to I. Because hopefully you can see that this has the largest I, middle I, smallest I. And so in terms of acceleration, that actually means this is going to have the smallest alpha, largest alpha, middle alpha. And so it tells us to go in order of increasing angular acceleration, which is really confusing to me. Maybe I'm just easily confused, because that means you need to start with the smallest and go up. So this has the smallest, this has the middle, this has the largest. For the record, this one actually has 2 masses rotating, whereas this one only has 1, so you may be like, doesn't that cancel out the fact that the radius is 2 times larger? No, because the radius is squared. So this one's I is like 2mr squared, and this one's is m2r squared, so it's 4mr squared, just for the record. All right, moving on to number 9. A saw blade accelerates from rest to 3,000 RPM in 1.25 seconds. If the blade has a radius of 15 centimeters and a mass of 300 grams, what is the torque of the motor? Assume the blade to be a uniform disc. So the deal here is we're going to... Why am I so easily confused? Okay, the deal here is that we're solving for torque, which is a relatively simple equation. The problem is A, they've given us a bunch of things we have to convert, boo, and B, there's an extra step that, you know, we never like extra steps. But let's just get started. So we know that torque equals I alpha, which is great. They tell us it's a uniform disk, which again, this is a really good one to know. It's 1/2 mr squared. So if we plug that in over here, we get 1/2 mr squared alpha. Okay, so now we have a formula for torque. So let's look at what we've been given. From rest, that means omega I is 0, to 3,000 RPM, which means omega F is 3,000 RPM, except we don't use RPM. And it's not just as simple as multiplying by 2 pi, because that would take us to rads per minute, which is not what we want. We want rads per second. So we have to multiply by 2 pi, and then we have to divide by 60 to go from minutes to seconds. I know you're all going to plug this into your calculator for yourself, but it is, I can't read my own handwriting. I think that says 319 rads per sec. Non-zero chance it says 314, but I'm going to go with 19 because I don't feel like rechecking my math. Yes, I worked all of these out before I recorded the video, and now I'm working them a second time. That's how much I love you. It's so much. Oh God, I'm really weird. Oh wait, okay, so this is, yeah, these are the things we're given. I am really weird. Other things we're given are that the radius is 15 centimeters, which I'm going to go ahead and convert to 0.15 meters. Guys, you really need to be able to do that conversion. Pro tip. Mass, 300 grams, is 0.3 kg. 3 decimal places. It's also a good one to be able to just rattle off. So let's look at what we've been given and what we have. Oh, and we've been given a time. T equals 1.25 seconds. So we have m and r squared. We can get I. Awesome. We do not have alpha. We do not know the angular acceleration. We have these 3 things. What does that look a whole lot like? Wow, Ms. Schneider, that looks a whole lot like kinematics. When alpha is what we're solving for, and angular position is what we don't care about. Yay! So we get to use the easiest of the kinematic equations. Omega F equals omega I plus alpha T. What was that number? 319 equals 0 plus alpha times 1.25. If you divide that out, you get that alpha equals 215 rads per sec. And then once we have that, easy peasy lemon squeezy, we can solve for torque. 1/2 of 0.3 times 0.15 squared times 215. That got kind of messy. My apologies. Plug all that into your calculator, and you get torque equals 0.85 Newton meters. I don't think we ever actually talked about this. This has units of Newton meters. Torque does. Because remember the very first equation we wrote down for torque was RF, so we were multiplying newtons and meters. That's where that unit comes from. It's not special enough to get its own units. Now, let's look at some more exciting, and by exciting I mean difficult, applications of torque, because it can be used in a lot of the same ways that force is used. So, if a mass is connected to a string that is wrapped around a heavy pulley, oh, our pulley is not massless now. This means it has rotational inertia that we're going to have to care about. Well, that sucks. It rotates on a frictionless axle. The acceleration of the falling mass will be less than or equal to the acceleration due to gravity. Well, let's think about that. Normally, when this was massless, the only thing gravity was having to act on was just the mass. But now we have rotational inertia. Inertia is resistance to motion. So it's going to, the acceleration is going to be less than that of gravity because it's having to pull the pulley and the mass downward. In the space beside the picture below, draw the free body diagram for the pulley and the falling mass. So, the falling mass is easy. Hopefully you remember how to do free body diagrams. It has weight pulling down, and it has the force of tension in that rope pulling it up. The pulley's free body diagram is a little weirder because this is distinctly not acting on the center of the pulley. The force due to tension is acting tangentially to the pulley, which is going to create a torque. There's also another force that's coming like from the axle. Something is keeping the pulley itself from not falling off the wall. So there's some like other force, but we really don't care about that. I probably won't bother to draw it in the future. I guess it's worth knowing that it's there. In cases such as the problem above, where the tension and the radius vectors make a right angle to each other, the net torque on the pulley is R times F. So again, the torque created here is going to be the force of tension times the radius of the pulley. The net torque acting on the pulley causes an angular acceleration, alpha, which can be related to the downward acceleration due to gravity, A, using the acceleration. It's going to look very similar, or it's kind of the opposite, actually, of this. This comes from much earlier in the packet. A equals R theta, so long as the rope does not slip on the pulley. That was true for things when we looked at things that were rolling earlier, like V was equal to R omega as long as nothing was slipping. Luckily, in AP Physics 1, we don't care about slipping. AP Physics C, you do care about slipping, and it's awful. It's just the worst, let me tell you. Let me go ahead and warn you right now that I did not really leave you enough room to work these next two problems. You might want to do them on separate paper. I have handy dandy separate paper because these are basically those fancy force problems that you guys loved so much, except now there's also torque involved. Again, great review. Unpleasant to look at, but great review. So a mass of 100 grams, which is 0.1 kilograms, hangs from an 800 gram pulley, 0.8 kg, with a radius of 10 centimeters. So that means R equals 0.1 meters. I'm just doing these conversions to begin with. As shown below, treat the pulley as a uniform disk. That means we know that it's going to be, its moment of inertia is 1/2 mr squared. Find the tension in the string, find the angular acceleration of the disk, and find the angular speed of the disk when the mass hits the floor. So we're looking for f of t, alpha, and omega f. All right, what's the first thing you should do in a problem like this? Wow, Ms. Schneider, I bet we should draw a free body diagram. We sure should. It's literally the same case as above, so we're again going to have oh, and let's refer to this as object 1 and this is object 2. That's going to be important later. Let's have this be our positive direction in terms of acceleration and speed. And then pulling up is f of t. Here, pulling down is f of t. And these are the same f of t, guys, because it's the same string. So we can write out equations for the sum of the forces acting on this object and the torque acting on this object. We can't really write out the sum of the forces acting on this object because we do have that other mystery force that we don't care about. But again, we don't care about it, so there's not a problem. So, the sum of the forces on object 1, so we'll call this F1, is going to be FW minus the force due to tension. Oh, and I super should write out that this is the force due to tension, this is the force due to gravity, but I'm not going to because I don't want to make this video even longer than it needs to be. So we have this, and we know that all of this equals ma, and that the a is going to be less than gravity because we have the pulley involved. The net torque acting on this object, on the, that's not a t, that's a tau, acting on the pulley is going to be r times the force of tension. This, our mystery force, does not cause any torque because it's located at the lever arm. So torque is always lever arm times force. If it's at the lever arm, it's not applying any torque. That's why if you just try to turn a lug nut with your hand, it's not going to work. It's not going to work out for you. You're going to be unhappy. And we happen to know that torque is also equal to I alpha in the same way that force is equal to ma. And we just wrote some things about both I and alpha. We know that alpha is 1/2 mr squared. And if you look back up here, we said that A was equal to R alpha, which means that alpha is equal to A over R. And you're like, Ms. Schneider, how would I ever know to plug that in? Well, because we're trying to think about these two equations together to solve for f of t, and we want as many unknowns as we can. So since this one has A in it, let's put A in this one instead of alpha as well. That makes some things cancel out rather prettily, because this cancels out 1r, but then now we have 1r on this side of the equation and 1r on this side of the equation. That's lunch. Alright, so pretty sure you guys just heard Ms. Brand come tell me that it was lunchtime, but I'm actually foregoing lunch today to keep working on this for you. So, sorry. I think what I was saying was that, so you have one of these r's cancels out the squared, and then the other r cancels out with this r all the way over here, so that we can actually rewrite, we now have two equations. We have f of t from this equals 1/2 m, and this is the mass of the pulley. Let's label that m2a. And then from this up here, if we rearrange this, we get f of t equals fw minus m1a, and fw is actually m1g. That is m1a. So you may notice we have two equations now with two variables. That sounds an awful lot like a system of equations. We can just set them. There are multiple ways you could solve for things here. You could solve for either a or f of t. Even though f of t is one of the things we've been asked to solve for, it's actually going to be easier at this point to solve for a, and we're going to need it anyway, so that's what I'm going to do. So I'm just going to set these two equal to each other. So 1/2 m2a equals m1g minus m1a. Oh hey, you know what would be fun, and by fun I mean awful, if we solved that in variable form before plugging in numbers, like this was an EP problem that didn't have numbers. So what would we do? We would have 1/2 m2a. If we want to get the a's together, we would have 1/2 m2a plus m1a equals m1g. If we pulled the a out of that, we would have 1/2 m2 plus m1 equals m1g. So if we divide all of this crap off, we have a equals m1g over 1/2 m2 plus m1, which is not fun to look at, but that is a reasonable answer for like an AP problem where they don't give you numbers. We do have numbers, so we're going to plug them in. We're going to say, let's see, m1 was 0.1 times 10 over 1/2 of 0.8 plus 0.1. So 0.1 times 10 is 1. 1/2 of 0.8 is 0.4 plus 0.1 is 0.5. So we have 1 over 0.5, which gives us, oh, you can't see anymore, which gives us 2. Oh, no, this isn't. I was starting to write 2 rads per second, but this is actually, this is linear acceleration. This is 2 meters per second squared. So that heavy pulley is slowing things down a lot, because normally it would be falling at 10 meters per second squared, and it's falling at 2 meters per second squared. All right, so now that we have that, we can go back and plug it into either one of these equations to find what they actually asked us for, f of t, force of tension. This one's shorter, so let's use it. F of t equals 1/2 m2a equals 1/2 times 0.8 times 2 equals 0.8 newtons. So we solved part A, you guys. Although, like, this hot mess was the hard part. Setting up these two equations and then derping out an answer for A. I mean, the majority of the problem is done. The next thing they ask us for, if we look back, is angular acceleration. And when you know linear acceleration, angular acceleration is easy peasy lemon squeezy. Because I'm trying to make the paper not tilted for you guys, and I am struggling. Whatever. Alpha is A over R, which we used up here. And now we're just going to use it again. So we're going to say 2 divided by 0.1, because the radius was 0.1 meters, equals, I just almost said that that was 0.2. It's not how math works. 20 rads per second. Makes more sense. Gets it. Oh, rads per second squared. I am all over the place. Clearly, I kind of needed to go eat. All right, the last thing they asked us for was omega final. Pretty much when you see omega final, like, you should know there's going to be some kinematics involved. Here's the problem. You're going to be tempted to set up rotational kinematics, and you're going to be like, omega I is 0, omega F is what we're solving for, delta theta alpha t. We just found that this is 20. The problem is that we don't know the rotational position, angular position, and we don't know time. But we do know something else from the picture. We know the linear distance. So we're actually going to need to do linear kinematics and then convert. So it's going to be VI is 0, VF is what we're solving for, D is 0.5 meters, A is 2 meters per second squared, and T is what we don't care about. So we're going to use VF squared equals VI squared plus 2AD. VF squared equals 0 plus 2 times 2 times 0.5. VF squared equals the square root of 2. VF equals 1.41 meters per second. And then pulling that back up here, there is a relationship between these, the same kind of relationship that's between omega and A. It's going to be VF over R. Yeah, just making sure. 1.41 over 0.1 equals 14.1 rads per second. Please excuse my terrible units. All right, number 6. 100-gram mass is used to pull a 50-gram cart across a table as shown below. The cart may be assumed to have free-moving lightweight wheels. Assuming the pulley is massless and frictionless, find the acceleration of the system. So that is old school. We can do that. So let's draw our FBD. Weight's pulling down. Tension is pulling up. And this is object 1. And then we'd also have to draw a free body diagram up here, where tension is pulling this way. The weight of this thing is pulling downward as well, but that's not going to be important for us. So let's set up our equations. We're going to have the net force on this block, F net 1, equals Fw minus F of t equals M1A. The net force on the second cart, or on the second object, the first cart, is only Ft. And that equals M2A. And they have the same acceleration. So if we solve both of these for f of t, this one's already solved for f of t because f of t equals M2A. But this one needs to be rearranged. It needs to be rearranged to say, just like in the last problem, it's going to be Ft equals, it's going to be Fw, no, yes, Fw minus M1A, but Fw is M1G, so I'm just going to write it that way. This is exactly the same as it was in the last problem. So we're going to set those two equal to each other. We're going to solve for A. It's going to be the same equation for A that we just used, which is M1G over I just confused myself, you guys. It's not exactly the same. It's not exactly the same because we don't have the 1/2, because we're talking about another object and not a pulley. Don't let me say things that are wrong. This is what happens when you guys aren't here. So there's a 1/2 missing that was in the other equation. It's just M1G over M1 plus M2. And that's just from setting these two equal to each other. I'm skipping an algebraic step. I'm going to let you do that on your own if you want. The mass had, the block had a mass of 0.1 kilograms. The cart had a mass of 0.5. So this comes out to 1.67 meters per second squared. So that is the old school, no rotational anything answer. Now the second part says the pulley is still frictionless, but now it has a mass, which means that it has a moment of inertia. It has rotational inertia. It's going to slow things down. So it wants us to find the new acceleration. One thing we can say right off the bat is that it's going to be a smaller number because that pulley is just adding things in that slow things down. So this was all A. So let's think about part B. Now we have, let's go back to our diagram. We have a third object, which is the pulley, that has its own free body diagram. The pulley's free body diagram is really odd looking though, because it has F of t here and F of t here. But guess what? You know how I was always like, same string, same tension. That's not true when you have a pulley that you're accounting for the mass of. Because again, over here, the pulley hasn't slowed things down yet. Over here, it has. Like, there's a difference. So we're going to call this F1T and this F2T. I know, some of you out there right now hate me. That's okay. I mean, it's not okay. I'm not happy. I don't like hurting you. What am I saying? All right, so now it's going to be very similar to what we did in the last one where we set up systems of equations, and very similar to what we just did here, but we have an extra one. We don't care about the forces really here. We care about the torques that these forces cause. Torque 1 and torque 2. So let's go. So F1 is going to be... Alright, so there was probably just a super awkward transition because this current software I'm using will only let me record 15 minutes at a time, and I super hit the 15-minute mark and didn't realize it. So I believe when I left off I had just started writing this. So what this says is that the sum of the forces on object 1 is weight minus tension 1 equals M1A. This is actually exactly the same as it was up here. That has not changed. What has changed is that now when we do the sum of the forces on object 2, which is our cart, it's still just coming from tension, but now it's a different tension. Tension has a different value. So we have that. And then lastly, when we care about the pulley, we're not going to care about forces, we're going to care about the net torque. And the net torque is going to be, because the pulley is going this way, so we're going to do what I've written as torque 1 minus torque 2 is equal to I alpha. So now we have a bunch of things that we need to try to plug in other stuff for. So let's solve things in terms of other things. That was not a clear sentence at all. Like, let's get this in terms of FT1. It's going to be FT1 equals M1G minus M1A. All right, this is already in terms of F2T, so there's not really any rearranging we need to do here. We can do some subbing in here. We know things about these torques. They're coming from these forces, and they're related to those forces by the formula torque equals radius times force. So here we can say the torque 1 is the radius of the pulley times Ft1 minus the radius of the pulley times Ft2. I here is the I for the pulley, which is a disc. So it is 1/2 M3, because it's the mass of the pulley that matters here, M3 R squared times alpha. So what we're going to do is we're going to take this equation and we're going to plug these two equations. Those are actually those arrows in the wrong places. This one goes here, that one goes there. We're going to plug those two equations in for those two tensions, and it's going to make a really giant mess of an equation, but it's actually only going to have one unknown, which is the important part. So let me show you what I mean. We're going to have R times Ft1 is M1G minus M1A minus R times M2A, because it's that, equals 1/2 M3 R squared, and then remember alpha is equal to A over R. So that's great looking, but a couple of things happen right off the bat, same as it did in the last problem. Those radiuses cancel out, those radiuses cancel out. So for the acceleration, the radius of the pulley actually doesn't matter. It doesn't play a role. we'll see in a second when it does play a role. And that leaves A as our only unknown, I believe. Let me rewrite this hot mess. Okay. M1G is the only term that doesn't have A in it. So we're going to have 1/2 M3A, and then since this was a minus and we're moving it over, it's going to be a plus M2A. This was minus and we're moving it over, so it's going to be a plus M1A. So if we pull A out of that, it's 1/2 M3 plus M2 plus M1. So we get, and then we divide all of that. You can't see what I'm doing. We divide both sides by all of this hot mess. And I'm going to rewrite that completely, and it's going to be M1G 1/2 M3 plus M2 plus M1, which, like I said, looks messy, but those are all numbers we know. Look how similar this is to the formula we got for acceleration here and the formula we got for acceleration in the last problem. It's just what's going in this denominator is changing depending on what else is involved in the problem. Okay, masses. The mass of our block is 0.1 times 10. 1/2 M3 is the pulley. How much does the pulley weigh? Oh, it's also 0.1. Plus, the cart is 0.5. Plus the block again, so 0.1. So plug all of that into a calculator, and we get 1.54 meters per second squared. So that is, in fact, smaller than the acceleration we got when we pretended that the pulley had no mass. So we can feel reasonably confident about our answer. It's not a huge difference. That's why a lot of the time it's okay, especially they design pulleys to be as lightweight as possible, because the smaller, if you look over here, it's already only half the mass of the pulley that matters. And so the smaller you can make that number, the smaller the difference is, and the easier you can just pretend that that's the acceleration, which is what we do most of the time. All right. What even else does this problem ask us? It has a million parts. C. For the case where the pulley has mass, find the tension in both segments of the string. Okay, so it just wants us to go back and plug in for FT1 and FT2, which is easy now that we have acceleration. We're using these two formulas here. FT1 equals M1G minus M1A equals 0.1 times 10 minus 0.1 times 1.54, and that gives us 0.846 newtons, and that's, I'm pointing at things you can't see, that's down here because both the pulley and the weight are sort of contributing to that tension. Then we solve for FT2, which is just M2A, 0.5 times 1.54 equals 0.77 newtons. So there's our tensions. And again, the tension here is less because it hasn't gotten to the pulley and the interaction with the pulley yet at that point, because that's kind of where motion starts. Part D, explain the importance of the cart having lightweight wheels. Well, let's think about all this hot mess that we just did. That was part C. Why did we have to do all of this? We had to do parts B and C because the pulley had mass and added rotational inertia that we had to care about. If the wheels had a lot of mass, we'd have to care about their rotational inertia. And that would be bad because it would make things even more complicated. All kinds of complicated. The mass carts that I have, all of anything that's designed for physics is designed, the wheels are going to be really lightweight, especially compared to the rest of the vehicle, so that you can ignore them. Rotational inertia. Alright guys, I'm sorry this video ended up being as long as it is. I really appreciate you sticking it out into the end. I hope that you feel like you've learned about torque. Maybe you even feel like you've learned something about forces, since some of you still haven't taken that test and it's just super important to physics. So if you made it this far, the secret code word is periwinkle. Don't tell anybody.